Hello and welcome to Maths Visualised. This video is part of a playlist covering differentiation. In this video we're going to be trying to build a solid understanding of differentiation through differentiation from first principles. This video is split up into its sections in the timeline. Right, so feel free to skip ahead if you already know this, but it's probably a good idea that we discuss the concept behind differentiation before we get started with differentiation from first principles, but it's your choice. Let's start with a line of y in terms of x. When we're differentiating this, we get a line of dy by dx in terms of x, where dy by dx simply means gradient. So it's best, or at least for the moment, it's best for you to think of the differentiated line as the gradient in terms of x. Let's say we have the curve y equals x squared minus 4. We can actually work out an equation for the gradient through differentiation, which we're going to take a look at in a second. But just for now, believe me, the equation for the gradient is y equals 2x. Basically, what this means is that if you were to draw a tangent to our first curve at the point x equals 2, we'd find the gradient is 4. Now looking at the gradient of our second graph for x equals 2, we also get the gradient is equal to 4. This will work for any value of x. So the reason we use differentiation and not drawing a tangent to a curve is because firstly it's far more accurate, and also you don't have to draw graphs, and realistically who likes drawing graphs? Differentiation from first principles is just the proof behind differentiation, so I'll go through an example to show you what it means. When watching this you won't get it first time around, so just stick with me in order to get the overall idea, and then I'll tell you once we're done, and then you can go back and watch it a second time, pausing it as you go. Also, if you're finding this video useful, a like would be greatly appreciated. In this example we're using the equation y equals x squared, nice easy equation just to get started. So we're going to be finding the gradient at this first point. The actual gradient is the tangent to the curve, but for differentiation from first principles, we approximate the gradient by drawing a line between this first point and the second point. We do this because we can work out the actual coordinates since they're on the curve. So it's probably not making sense just yet, but just stick with me, as hopefully by the end it will do. So each of these points have coordinates x1, y1 and x2, y2 respectively. I could have used A, B, C and D, but I prefer to use x1, x2, y1, y2 because it makes more sense to me. So in order to find the gradient of a line, we do rise over run. In this case it's y2 minus y1 over x2 minus x1. If we go back to the graph, we're going to say our value of x1 is x, and we're going to give the gap between x1 and x2 the value of h. This means that we can say x2 equals x plus h. We know y1 equals x1 squared because the equation is y equals x squared, and since x1 equals x, y1 must equal x squared. Finally, if we know y2 equals x2 squared and x2 equals x plus h, it means that y2 equals x plus h all squared. Now that we've found all of our values for x1, x2, y1, y2, we can now sub them into our equation for the gradient, and we get x plus h all squared minus x squared over x plus h minus x. That all simplifies down to 2x plus h. So we're nearly done now, but in order for our approximation to be as good as possible, we need the gap between the first and second point to be as small as possible. As we move the second point closer to the first, the line becomes closer to a tangent, meaning it's a better approximation. Now, if we watch this again, you'll notice that h is actually getting smaller, and in order to get the best approximation possible, we want h to be infinitely small. So if we go back to the equation, we can say limit h to 0, because, as I said, we want h to be very small. Then, as our final step, because h is so close to 0, we can effectively say it does equal 0. Meaning that the gradient is equal to 2x. If you ever need to do differentiation from first principles for a different equation, all you need to do is sub in the relevant values for y2, y1, x2 and x1. Now, you might want to go back and have a second look, so I've put the time on screen. Now that we've done that, it makes sense to tell you that the d in dy by dx actually means very small change. So you could just say dy by dx as very small change in y over very small change in x, which is basically rise over run on a very small scale, which is what we just did. One other thing, the general equation for differentiation from first principles is written like this, which is actually the same as what we have just done, but it's written using function notation and then simplified. Personally, I find it much easier to think about it the way I explained it, but if you want to use this, you can. Thanks for watching this video. If you have any questions, please do leave them in the comments. Also, if you found this video useful, please do consider leaving a like, and if you have some friends who might find it useful, please do tell them. I mean, unless of course you want to beat them in a test, in which case don't tell them, but thanks and bye.